All right, let's get started for today. So, a couple of announcements. Your homework 5 has been released as of Monday night. It's due on Monday at midnight. Your project 3 will be released very soon. It's about MDPs and reinforcement learning. And that will be due next week, Friday at 5. An announcement that's not directly part of the class, but since you're in the AI class, it might be of interest to you. There's an interesting talk about AI today at Berkeley, which is part of a recruiting session from Baidu. It's at 1:30 in the Wozniak Lounge. Title is What's Happening in Deep Learning, AI Without the Hype. This is a talk by Andrew Ng, who actually was my PhD advisor, and Adam Coates, who was a student at the same time as I was a student in Andrew's group. We worked together on a lot of projects. Andrew's, at this point, pretty well known for quite a wide range of projects, including he started the Google Brain project, he started Coursera, and one of the most well-known and advanced demos we'll see in lecture today is also from Andrew's group. So if you're interested in AI, especially the machine learning side, and you have the time, I recommend going to this session. You'll probably learn a lot. Any questions about logistics? Okay, then let's take a look at some AI in the news. This is from about a year ago, but very related to what we're doing in today's lecture. There's this game called Flappy Bird. Very simple game you can play on your phone. About a year ago, somebody formalized this as a markov decision process and ran QLearning on it to see how well it could do. So the state space they picked was discretized vertical distance from the lower pipe, discretized horizontal distance from the next pair of pipes, and then you could be dead or alive. The actions available are to click, which kind of propels you up a bit, or do nothing. The reward was +1 if still alive, so encouraging to live longer, and -1,000 if dead. Then they ran 6 to 7 hours of QLearning on this MDP, and here is what you get. Let's save this. So it actually works pretty well. Okay, staying alive for the remainder of lecture. At least the part we see. Okay, any questions about logistics? Let's get started with the technical part. So what you've been looking at last week is a continuation of covering markov decision processes and reinforcement learning. Today we'll see more reinforcement learning. We'll address some of the remaining open problems. Let's first take a look at what reinforcement learning is about. So we still assume there's a markov decision process. What does that mean? You have a set of states, a set of actions for each state, potentially. A model, TSAS prime, is, in this case, T is a three-dimensional table with an entry for each state action state triple, and the number TSAS prime is the probability if you are in state S and were to take action A that you end up in state S prime. Then the reward function is also a three-dimensional table, one entry for each state action state triple, and it's encoding if you were in state S, took action A, and landed in state S prime, what your reward would be. In reinforcement learning, we still have an MDP. We're still looking for an optimal policy pi. The new twist is that we don't know T or R ahead of time. All we get is a system to interact with. And maybe through interaction we can still find a good policy, but we can't directly apply the standard methods to solve MDPs because those standard methods assume you have the entire MDP available to you. So one of the main ideas here was that from experience, you can compute statistics over what might happen if you act in a certain environment and get, in that way, proxies for either T or directly try to find a good value function. So to summarize the different kinds of techniques you've covered so far, there's two big categories of problems you could be in the case where your MDP is known versus unknown. If your MDP is known, you can solve it ahead of time. You don't need any interaction with the system to solve it because you have the full MDP description. You can then, if you're interested in the optimal value function, optimal Q function, or optimal policy, run either value iteration or policy iteration. Both will give you the optimal policy and optimal value function, optimal Q function. Alternatively, if all you're interested in is evaluating a fixed policy pi, then you can run policy evaluation to see how good that policy is. And this can all be done offline. And then once you have the optimal policy, or maybe just a policy that you evaluated, you can decide to act in that system and collect your actual rewards as you act. Now, if the MDP is unknown, there's a two-way split here. There are two different families of techniques in terms of how you can still solve this problem. The most straightforward in some sense is model-based. Model-based means that even though you don't have a model ahead of time, you're going to collect statistics by acting in your MDP. And from those statistics, you will build an approximation of the real model. You'll use that approximation to then use the same techniques that we had up here. Will you find the optimal policy and value function? Probably not exactly, because your model will be approximate, but the more experience you collect, the more accurate your model will be, and the more accurate the value function, Q function, and policy that you find with the approximate model will be for the real thing. Now, you also saw that you can actually completely bypass modeling. Instead of first modeling and then in that model computing the optimal policy or value function or Q function, you could directly from samples estimate the Q function or the value function or both. If we want V star, Q star, and pi star, we can run QLearning, which we'll see a lot more about today. If all you care about is learning a value function for a fixed policy, you can run value learning. Now, keep in mind, we won't get back to value learning in this lecture. Once you run value learning, all you get is the value of the policy you were evaluating. It doesn't tell you how to now improve your policy, because if you wanted to do something like policy iteration, which also starts with an evaluation, you actually need a model of your MDP to be able to compute an action that's greedy relative to the value you just found. So if you just do value learning, you're kind of stuck there. You can't get to a better policy. Okay, this class here, it's a class of algorithms called model-free learning, and we'll look at that for the remainder of this lecture. Now, temporal difference learning was this idea that the way you can do model-free learning is by looking at sequences of experience in your system, and then for each state, action, reward, state, quadruple, you would perform an update. And that update would effectively mimic the Bellman equation. The Bellman equation tells you something about the value of the current state is some function of the action you take, as well as then some expectation over reward you would get and value in the next state. Now, since we don't have the model, we cannot compute this expectation, but since we get experiences, we get samples, we can approximate that expectation based on these types of samples. Okay, so the core here is experiences of this type, where you get a state, you are in a state, you take an action, you get a reward, you land in the next state. QLearning was in some sense kind of the ultimate thing you've seen so far. What does QLearning do? Well, these are the original Q value iteration updates. This is if you know the model, you can compute this for the Q value for state S and action A, assuming you have k plus 1 steps to act, can be computed as a weighted average over possible next states S prime, weighted by the probability of reaching that state S prime when taking action A in state S. And then what we are taking a weighted average of here is the instantaneous reward for the transition from S taking action A into S prime, plus then a discount factor gamma times the expected value from the next state, assuming we act optimally. That's what this max over A prime is doing here. So this here is over all actions A prime we can take in the next state S prime. We look at the Q values. If there are k steps to go, take the best one, and that's what we use in this calculation because we are trying to compute the optimal Q value here. Okay, so when we don't have T and R, we cannot directly compute this because T is sitting here and R is sitting here. What we can do instead is just look at samples and approximate this. Say, well, we saw an experience, we observed the reward, so we can get this part based on the observation. Gamma is assumed known, and then, well, we might have a running estimate of what Q could be, and we can fill that in as a substitute for the actual thing we want here. And now, together, we have an estimate of what's over here. We still need to average weighted by T, but we don't have T. What we do is we just average it over experiences we encounter over time. We can straight up average this because things that are more likely under T will more often appear in our sample set. Things that are less likely under T will appear less often in our sample set. So we can just straight up average these experiences to get effectively an average that's weighted by T. Okay. Now to keep the running average without having to keep everything around, we have this update over here. What is this saying? It's saying the new Q value for state S and action A is the old one over here, averaged with this quantity over here, which is our new sample estimate. Why don't we just take our new sample estimate? Well, we want to average over experiences. If we just take the last one, we override all past experience we've gotten, and we want to retain that in some way. You also saw that this is actually an exponentially weighted average, the way this is done, where over time, earlier experiences weigh in less than later experiences. And this is actually a good thing for two reasons. The first reason is that it's nice because you only need to keep track of your latest estimate, and you can then weigh in the new sample this way. The second reason this is really helpful is that by keeping track of this exponentially weighted average and having old experiences be less relevant to your final outcome, you actually downweigh things that are less accurate. Because when you start your computation, what you fill in here is not all that accurate. And as time goes by, it gets more and more accurate. It will be weighted more highly, and this is how you converge to the right value. Okay, what are some properties of QLearning? The amazing result is that QLearning converges to the optimal policy, even if you're acting suboptimally. That's a really important property. This is called off-policy learning. You can act according to one policy, but still learn the value of another policy. In this case, the other policy you learn the value for is the optimal policy. Let's take a look at this. So here is QLearning in action in a grid world. So it's running automatically here. QLearning is running. See, it's acting somewhat randomly. Squares that are still almost entirely black usually means that the agent hasn't been in those squares, hasn't collected much experience, and accordingly hasn't done much of an update in those squares. We see at this point that over here, let's see, can we get the cursor there? The middle row, actions that go to the right, have a pretty high Q value, but in those same states, for example, this state over here, while to the right has a high Q value, going to the bottom has a very low Q value. So it is possible in a given state to have Q values that are widely discrepant, because some actions could be far better than other actions for any given state. The other thing to notice is that as, for example, the agent jumps down this way in any of the executions, the values actually propagate back will not get worse, because anything that's here, when it looks at the future and does an update, it looks at the best Q value in that state. And so if it experiences something bad in a state, as long as there's a good Q value available, a better one, this will not affect the updates that happen to the predecessor states. All right, so that's QLearning in action. Now, there are a couple of caveats here. The first one is you have to explore enough, and we'll see more about that later, but effectively what that means is you have to visit every state action pair infinitely often to have these guarantees. Eventually, the learning rate has to become small enough, because if your learning rate is too high, your updates will be very significant when you see something that only occasionally happens, and you'll jump away from what you just were about to converge to, and so things won't average out the right way. You also don't want to decrease your learning rate too quickly. If you decrease it too quickly, then later things don't contribute enough, and you might not have collected enough experience to converge to the correct average. In the limit, it doesn't matter how you select your actions. That's the off policy part. It just matters that you see every state action pair infinitely often. Okay, so there's a big question here about visiting every state action pair infinitely often, getting enough experience, see what's out there. This is a big trade-off in reinforcement learning. Pretty much any paper about reinforcement learning, you'll see that as one of the main topics they'll look at. And it's really the same thing as if you just went for lunch today, and normally you go to the same place because you know that's your favorite place in Berkeley, but there's just something new that opened up. You're faced with a dilemma. Well, you know your usual place is pretty good, but this new place could be better, and until you've tried it, you're not going to know if you like that new place better or worse than the place you usually like to go to. And so there's this cost here that you need to try something out before you know whether it's better or worse than what you've seen so far. So let's see how we can formalize exploration. So the first scheme we'll look at is a random scheme. This is called Epsilon Greedy. What that does is that every time before you take an action, you flip a coin. That coin, with probability epsilon, comes out one way, probability 1 minus epsilon the other way. If it comes out the epsilon side, so to say, you act randomly. If it comes out the 1 minus epsilon side, you take the optimal action with respect to your current Q function. So if your Q function gets better and better over time, you'll more often do the right thing, but you keep infusing some randomness to ensure exploration. Let's take a look at how this plays out. So in this case, we're going to do the exploration ourselves. So agent starts here. Let's mirror that so you can see it too. Agent starts over here. I get to choose the actions from the keyboard. At this point, we can see some structure here, but keep in mind, a reinforcement learning algorithm would just know that there's a certain number of states, wouldn't know the connectivity of these states because it doesn't have a model, and it would just know it's in a particular state, and all Q values are 0 as they are initialized right now. Let's go left. Let's see. Let's go left again. Happens to be an exit state. Let's make sure we can see that value a little better. There we go. And so we got a reward, some kind of reward there that was positive. Let's continue playing. Let's go left again. Again, got a positive reward, and Q value gets updated. Now as we keep going left there, we see that we learned that going left is not bad, but we haven't learned anything about anything else. So let's explore something else. This time let's go right, and maybe let's go down, and that's an exit state, minus 50, not as good. But can't really blame ourselves for this because we didn't know before we went there what it would be. It could just as well have been plus 1,000. Until we've experienced it, we wouldn't know. Now that we've experienced it, maybe we don't go there again. We'll go somewhere else. Maybe let's go here. Again, not a great state. Got negative reward, but we couldn't know. At this point, we might look at this and say, well, it seems like the bottom row is pretty bad. I should never go to the bottom row again because there things seem to be pretty bad. But the QLearning algorithm that we've seen so far has no idea about those kind of concepts. It doesn't know about a bottom row. It just knows that there's a set of states. It doesn't know that some of them are together in a bottom row. Later this lecture we'll see how some of those concepts can be encoded into it, but at this point what we've seen doesn't know anything about that. And so it might then decide to take a random action here, go down there, and again, not that great. Maybe up is better, might try that. Not that great either. Maybe coming across is better. That's indeed better. Maybe we keep going that way. And we see, as we keep going that way, that these Q values propagate from left to right, from right to left as we visit states and do Q value updates for those states. Now here's something interesting. If we, from here, jump down and get a very negative reward, and now go again, ooh, it exits. If we go again, let's show that again. So if we do this in the very beginning, so let's say we go down all the way here, we get a positive Q function along that middle row. Then if, for example, here, we jump down, look at the value 3.12 for the preceding state, we go down, this is pretty bad. We play again, we visit that preceding state again, we go through that right action again, the value is still going up. Even though the previous time we went through that state, things went bad, it just looks at the Q value of the best action in the next state, which is a good Q value, and that's how it updates things. All right, so this was manual exploration. This is one way to explore. Let's now look at a demo where it's exploring for us. So this is the crawler. This is something you'll play with in your project 3. This is running Epsilon Greedy exploration. In this case, Epsilon is 0.8, so taking a lot of random actions. And it's learning a Q function, is trying to move off to the right, positive reward for velocity to the right. See, it's making some progress, but not a whole lot. Let's accelerate its progress by skipping a million learning steps, by doing it without watching it. There it is. It's done an extra million learning steps. It's doing a little bit better at this point. Our epsilon is still very high, so we might want to tune it down so it explores a little less and is a little more focused on picking the optimal action rather than the often taking a random action. And here we go, and it's off to the right. Now, what were some issues here? Well, the first one is that we have to make a decision when we tune down epsilon, right? When have we explored enough that epsilon can go down, or should we still take a lot of random actions? And then, of course, there's the issue of, well, what should epsilon really be? Should it be high? Should it be low? Should it be somewhere in between? Is just taking random actions really the right way to explore? Or is it a pretty slow way to potentially explore your space because you're just randomly moving around as opposed to targeting spaces that you haven't been to before? So let's take a look at a more advanced solution. So when do we want to explore, right? Random actions would just explore a fixed amount. Much better idea would be to say, well, I want to explore when there are things I don't understand very well yet. And whenever you have not seen a state action pair all that often, you try it out because you want to experience what it's like. This is a little bit of a reminder of what we saw in the lecture on utilities. If you've already seen something is pretty bad, there's no reason to keep exploring it. But as long as you don't know, you might want to try your chances. So this is a little more subtle than Epsilon Greedy. Let's take a look at what we can do here. So the standard Q function update looks like this. Right? Where this update here with the alpha underneath means that we are taking the current QSA value and taking a weighted average between the current QSA value and this new thing on the right-hand side, where alpha determines the weighting between the two. Here is a new update that will focus our exploration towards state action pairs that are relevant for exploration. So what's happening here? As our current estimate of the Q value of state S and action A, we still have the reward, we still have a discount factor, we still have a max over actions for the next state. Then we have this F here that computes some function of Q S prime A prime, and then this other thing N S prime A prime here. What is N, capital N S prime A prime? It's counting how often you have been in state S prime and taken action A prime. Okay? So if you look at this calculation here, you might need to put a little +1 here to avoid divisions by 0, but effectively what's happening is this F function is saying I'm taking the first argument, U, and I'm adding something to it based on the second argument. If the second argument is very small, I add something big to it. If the second argument is very large, I add almost nothing to it. So once we've experienced the state action pair as prime A prime infinitely many times, then we'll add k divided by infinity, which is 0 and nothing changes. If we've experienced it only a small number of times, we'll add a large number. So effectively what's happening here, it's saying that an action A in state S will become higher valued if it led to a state S prime from which exploration is possible that's of high value. Well, high value meaning we don't know very much about that state action pair S prime A prime. Now this has two effects. The first effect is that just for the state action pair SA, next time you're there, when you select your action, if you take the greedy action with respect to your current state, you will pick an action that is more likely to lead to exploration. But there's also cumulative effect over time. As you keep running QLearning, these, what you can think of as exploration bonuses, like extra value added for being able to reach these states S prime, state action pairs S prime, A prime, where you can explore, these exploration bonuses will propagate through your updates. And so you'll actually get a chaining effect there where as experience accumulates, you might say, well, if I'm here at the end of the hall, at my end of the hallway, I've never been, or almost never been to the other end of the hallway. There's a lot of exploration value there because I've almost never been there. That will have, after you've been there a few times, that will have propagated to the front of the hallway where you're at. And from there, you'll take actions that lead you to the end from where you can then explore that part of the space. And so you get a very directed exploration behavior here where you move towards parts of the state space that you have not seen very often before. Note that you need to have seen it at least once before, and typically a few times before, otherwise the values would not have propagated, but that's fine. Initially, just by randomness and having seen things 0 times, giving you a big bonus, you'll start seeing things at least the first couple of times, and then onwards things will propagate. It also means that there's some kind of trade-off here happening automatically. If a state is very negative reward, if something is really, 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 really bad, after you've seen it a few times, this exploration bonus might not outweigh how bad the real reward is. Similarly, if something is really, really good, very, very high reward, even if you've seen it many times, while you're still exploring other states, you might still already want to visit it because you know that even accounting for exploration bonuses in other places, that state action pair is really interesting to visit. So let's take a look again at our crawler, and now we will run it without needing to step a million steps forward. Let's see. So this is the crawler again. This case using still a little bit of randomness in its actions, but using an exploration function as described on the previous slide to guide its choice of actions to help it explore and exploit. So we see that it's actually, at this point, starting to exploit quite a bit more. Let's tune down the randomness completely and see how well it's doing. We see that I actually learned to make progress pretty quickly without needing to fast forward through a million iterations to get there. All right, you'll see a lot more of this in your projects 3. Let's go back to the slides. Okay, so there's a new notion here I want to introduce. It's called regret. What's the idea here? If you are a reinforcement learning agent and you have never seen something before, you don't know whether it's going to be good or bad. So if you want to learn to act optimally, you will sometimes experience something bad. You'll end up in a fire pit just because you didn't know it was a fire pit. Now, even though after running a reinforcement learning algorithm for a long time, you might find the optimal policy, you could still say, well, not all reinforcement learning algorithms are equal. An algorithm that needs to jump in the pit a million times before it succeeds is not nearly as good as an algorithm that can succeed needing to see it only once, so to say. And regret is a measure of how you compare these learning algorithms. In particular, what it measures is, during the entire learning process, what is your accumulated reward? What would have been your accumulated reward had you acted optimally the whole time? Take the difference between those two, and that's your regret. And so the better your reinforcement learning algorithm, the lower your regret will be, because the less the difference will be between what the optimal policy would have accumulated versus what a policy that still needs to learn that you were running has accumulated. Now keep in mind, your regret will never be 0, or almost never have to be a very special case, because you don't know what the world is like, and without trying things, you're not going to be able to learn anything. But the objective would be to keep the regret as low as possible. Okay, so that's exploration. Now there's another big thing we need to look at, which is how to perform approximate QLearning, which will be a solution to the problem of dealing with very large state spaces. So, basic QLearning just has a table of Q values, one Q value for each state action pair. So let's take a look at basic QLearning in action for PacMan. Here is basic QLearning in action for PacMan. Ooh, it's popping up on the wrong window. Let me get out of the presentation. It's still popping up over here. Let's watch this one in video then. Okay, here's our first demo. What are we looking at here? We have PacMan in a tiny, tiny little world. There's a ghost. Let's see if this video is willing to play. Here we go. Come on. So what we see happening here is that PacMan is running QLearning, is playing this game, and gets eaten by the ghost pretty much every single time. Sometimes it wins and gets high reward, it learns from that. Often it gets low reward, it learns from that too. It just takes a really long time to learn anything, even for this really tiny grid world. Now, if we fast forward this 2,000 episodes and watch again after 2,000 iterations of PacMan learning, here's what we get. It's doing the 2,000 training episodes, done with it now. It's taking the greedy action with respect to its Q values that it learned, and it's actually doing really, really well. So we see that PacMan is able to learn this, to play this game quite well. With QLearning, it just takes 2,000 iterations to learn to play, even in this tiny little world. If we look at a slightly bigger world, things are terrible again in terms of just here we don't even see PacMan succeed in the first several trials just because you need so much luck to succeed if you act randomly, and so it's still exploring heavily, doesn't have much chance of succeeding, it's not getting nothing but negative rewards so far, pretty much, so it's actually not able to distinguish a whole lot between the different things that happen. And so the big problem we're faced with here is that if the state space is large and you need to see every state action pair infinitely often, or in practice many, many times, it can take a really long time before you learn anything. So let's put this in words. Realistically speaking, if you have a reasonable reinforcement learning problem, there are just too many Q states to be able to visit them all many times, often even too many to just keep them all in memory, values for all of them. So that becomes impractical. So think of it as the difference between just needing to keep one small table in memory versus a whole library of books, so to say. So we can't really use the same technique anymore for realistic problems. Now, what we really want to do is learn from just a small set of experiences, things that apply to other states that we haven't seen yet, right? This is a fundamental idea in machine learning. Machine learning is all about you see experiences. You're never going to see the same thing again, most likely, because there are so many possibilities, but you'll see similar things, and you want to infer the right thing for those similar things that you've never seen before. All right, so let's first take a look at how naive our current QLearning is. Let's say we run QLearning in this particular scenario over here. And after running QLearning, we learn something about that state. Now we encounter a new state. And what does our Q value table say about that new state? If it's the first time you see it, it's still zeros if that's how you initialize things. So we'll know nothing about that state. Even though if we look at it, it's actually quite similar to the first state. And you'd hope that a good learning algorithm would understand that these are similar situations. If the first one was bad, the second one is bad too. How about this one? What's the difference between the third one and the first one? The difference is really, really tiny. The difference is just right over here, 1 foot pallet's gone. But as far as QLearning is concerned, that's just a different state like any other different state. Of course, you're all thinking that's not good and that's what we're going to fix. But keep in mind that standard QLearning would think of this thing, this third state over here, as completely different from the first one, and have no idea that because the first one is bad, the third one is bad too. Okay, so instead of representing the Q function as a table where every state action pair has its own entry, we want a representation that encodes some properties of the state, and based on those properties computes a value. In fact, you've seen this before. We call it evaluation functions in lectures 6 and 7. It's called evaluation functions. You would compute the value of a game state not by having a big table where you looked up for every possible game state what the value is, but you actually had some way of computing something approximate. So we'll do the same thing here. So we pick some features, for example, distance to the closest ghost, distance to the closest dot. number of ghosts that are nearby, for example, 1 over distance to the closest dot squared is PacMan in a tunnel, which could be a 0, 1 feature. Could be many more features. Could even be a feature that says, are you in the state that's shown exactly on this slide? Now, if you have too many of those, of course, you're back to the original scenario of having a full table of Q values, because for every possible state, you have a feature that says, is it this state? Then that becomes equivalent to not having features at all. But typically, you'd pick features that generalize better, like the ones shown in the list up here. But in principle, if there were a very special state you cared about, you could still put it in there and say, is the state I reached exactly this state? And then based on these features, we're going to describe how good a particular state is. So one way to do this is by taking a weighted combination. This is what we did in evaluation functions too. There was a slide there with a chessboard, weighted sum of features for evaluating chess situations. We can do the same thing here. It won't be an evaluation function, it'll be a value function or a Q function. The Q function is what we're most interested in this lecture. We can do the same thing for value functions. So saying our Q function will be a weighted combination of features. The weights we don't know yet. We'll learn the weights and we'll see how to learn them. But now when you encounter a new state action pair you've never seen before, you can use this parameterized Q function to compute an estimate of the value for that state action pair. Okay, what's good about this is it can generalize to states we haven't seen before. What's bad about this? Well, if you don't choose your features carefully, the feature values might be identical between two states where you want the values to be different. But once the feature values are all identical, the values will also be the same. So you need to be careful that if you want to be able to distinguish between certain states, that your features indeed take on different values so you can learn weights that indeed distinguish between those states. So how to find the weights? Actually, let's take a break here. And after the break, let's take a look at how we can learn those weights. All right, let's get started again. Any questions about the first half of lecture? Right, in the first half we covered exploration. Now we're looking at how to generalize using approximate Q-learning. So our Q function is now represented in this particular format, not a table anymore, but a weighted sum of features. Question is, how do we find the weights that are appropriate for whatever MDP that we're currently acting in? So let's assume we encounter a transition where we go from state S, took action A, received reward R, and landed in state S prime. Then we have the difference here between what we just experienced as our best estimate of the Q value for state S and action A, which is the reward we experienced plus gamma times, and then the max over A prime, QS prime, A prime, which is our best estimate of the value for the state S prime based on what we currently have. And we can take the difference with QSA, which is our current estimate of the value for SA. All right, then standard Q-learning would say, well, I'm updating QSA by adding on the difference weighted by some weighting factor alpha, because we don't want to go all the way to what I currently experienced. We want to just nudge it a little bit in the direction towards the current experience, because we need to average things out over experiences. Now, we don't have the Q values directly available, and we don't want to have them directly available because we want to generalize. So let's generalize this. Here is the update we can use for each of the entries in the weight factor. What is this saying? It's saying entry I, which is the weight we multiply with the ith feature in evaluating the Q value, gets nudged a little bit. Alpha is making sure it's not going too far. It's getting nudged. How? Well, there's a difference between the Q value we experienced, so to say, our current sample value and the one we wanted. We nudge it in that direction, assuming at least the feature is positive. So let's look at the simplest case first. Let's assume the feature FISA equals 1. Then the update is the same as it was before, except that it's now applied to the weight entry WI. The weight entry WI is nudged in the direction the Q value would have been nudged, and that's effectively when you compute your Q value with that weight vector, it will also nudge it in that direction. Now, what if Fi equals 0? Meaning that feature is in some sense inactive for the pair SA. Then Wi will not be changed at all. That's what we want, because even if there is an error in how we compute the Q value and we wish it was a different Q value, since this feature is 0, changing the weight cannot be done in a very informative way here, because the weight is just going to be multiplied with 0, have no effect on the Q value, so there's no point in nudging around the weight Wi if Fi equals 0. What if Fi is negative? Let's say -1. Then the nudging for Wi will be in the opposite direction due to the Fi being negative, but then when you use that weight, in some sense those negatives will work together nicely, and overall the Q value that you compute after the update will still have been nudged in the direction you want to nudge it by this update. Now let's look at the more general case. It could be any value, let's say any positive value. What you see here is that the larger Fi, the bigger the update that will happen to Wi. Why might this be desirable? Well, if a feature value is very high, you can think of it as, well, that feature is very active in this particular state action pair. Sometimes it's capturing most of what's happening in that state action pair compared to these other features which might have only very low activation, for example. And so the features that are most active will get their weight nudged the most to make up for the difference that we're experiencing here. If it was a large negative value, the same thing would happen. It would just nudge it in the opposite direction, and together things would cancel out. So that's the intuition here. The bigger the feature, the bigger the weight update. The feature in the extreme case is just equal to 0, weight will not be updated at all. So that's the intuitive interpretation. It turns out there's also a more formal interpretation we can make here in terms of online least squares, which we'll see after we've seen a few examples. So let's look at an example. For PacMan here, we have a Q function of this format. There are two features, one related to the distance to the nearest dot and one related to the distance to the nearest ghost. The weights are 4 and -1, so we have, in this case, W1 equals 4, W2 equals -1 currently. Then we are in some state. We take some action, in this case north, experience a reward of -500. The Q value, when things are over, is 0. Game is over. The expected sum of rewards from there onwards is 0. We can use this information to perform an update, as we saw in the previous slide. So we first compute the sample value over here. Then we look at the difference, which is -501. Then we make an update to our weights, which is we have the nudging factor alpha, we have the difference, and then we have the feature value 0.5 for the first feature and 1 for the second feature. Then we get a new set of weights. Accordingly, we have a new Q function. And note that the Q value actually has changed for all states in this case. Any state you could be in, essentially, the Q value has changed because the weights have changed, and it affects any state where those features are non-zero. Okay, let's take a look at PacMan running approximate QLearning in a pretty complicated scenario. You'll get to do this for your project 3. So here's PacMan running approximate QLearning. It's learning that dots are good. Oh, it died. Oh, it's doing the same thing where it's always showing it on my screen. All right, let's look at the recording then. So initially, PacMan has all Q values equal to 0. Then once it starts playing, what we'll see is that it'll update its Q values when it encounters a positive dot, a positive score thanks to eating a dot, Q values go up. When it encounters a ghost, Q values will go down. So here, first experience, it now learned dots are good, ghosts are bad, but the ghosts were unavoidable here. It knows dots are good and ghosts are bad, so it's running away from the ghost at this time. It's never been in this state before, but it knows what to do because it has a Q function representation that generalizes. You see it actually in just its third episode already won the game from just playing twice before. It's never experienced eating a power pellet, so it actually doesn't know that's a good thing. Ideally it would explore that, but it's not exploring that in this particular case. All right, so what just happened here is that we saw PacMan learn to play the game from just essentially 2 episodes of playing. There are features related to how far the dots are away, how far the ghosts are away. In fact, there were no features here for the power pellet, so it couldn't really have learned anything about them, even had it experienced them. But this is very different from what we saw earlier, where we needed to fast forward 2,000 learning episodes in a PacMan grid that was just 2 by 2. Okay, let's now see how we can formalize what we just did. So we'll do this based on least squares. We won't see a super formal version of what we looked at, and this is a little beyond the scope, just a couple of slides of what we'll expect from you for this class, but I still want you to have the intuition of what's underneath. So least squares, what does that do? You get a bunch of points, you try to find the best line through that bunch of points. What you do is say, well, effectively I'm trying to make predictions of values on the vertical axis. My predictions y hat are based on some intercept term w0 plus some other factor w1 times my horizontal coordinate f1 of x. This assumes there's just one feature here, right? So, and the way you do it is, you can do this in many dimensions. You effectively just say, well, my prediction is a weighted combination of features, and you put your features on all the horizontal axes, or in higher dimensions you can't try it, and then the vertical axis is what you try to predict. The way you measure how good that set of weights is by measuring the residual. This could be the predicted y values for each feature value, and the dots are the samples, and we can measure how far the samples are off that line. The further they are off, the worse, and we want to find the line in this case, or in general the linear function approximator that fits the dots as well as possible. Okay, so how do we measure this? We look at the actual sample values yi and compare it to our predicted values y hat I at each of the sample points. The predicted values we have an equation for. We know that this is what we use, a weighted combination of features. And so we want to somehow find a set of weights w such that this thing is as small as possible. In fact, we've already seen a way to do this, right? In the second lecture where we on the topic of CSPs, we saw something called hill climbing, where you would effectively have a current setting, a current choice of your variables, and then you would look at changes to those variables, see if they're better or worse. If they're better, you might keep them. If they're worse, you discard them, and so forth. So we could, in principle, do the same thing here, but we'll do something slightly more sophisticated. Because we have continuous variables here, you can do something that's a little more informed than just changing values and see if they're better or worse. So one way to minimize error is to just look at one error term at a time for now. So we have just one example x, and we want x to map to y, and we somehow want the weights to be such that that happens, right? So we can say, well, if we want to look at how we can improve the weights, we take the derivative of the error term with respect to the weight entry wm, right? If that derivative is positive, that means as you increase w, you will increase your error. If that derivative is negative, that means as you increase w, we will decrease your error, right? That's what the derivative does. It tells you locally whether increasing wm will also increase your function value or decrease it. With that information, you can now decide in which direction you should move W, right? If the derivative is positive, we know we want a low error, then we want to move in the negative direction. If the derivative is negative, meaning increasing W decreases error, we want to move in the positive direction. But it also tells us a little more. It also tells us the slope of how much the error will increase or decrease as we change W. And so a more sophisticated update, rather than just nudging in that direction, positive or negative based on the sign of this derivative, would be to actually use the derivative itself, just over here, to decide how far we update. Simplest case, let's say this derivative is very, very negative, right? What will happen then? So let's start here. Let's say this derivative is very, very negative. What that means is that if we increase Wm, the error will go down. So what do? We have this negative, very negative value here. If we increase Wm, value will go down. We want to increase it, so we actually take away this negative sign here, get rid of it, flip the sign effectively of our derivative, and here is our update, which is now saying move a large step, because our derivative is large in absolute value, in the positive direction because the derivative was negative, which means we should move in the positive direction. All right, so this is effectively nudging that line by adjusting one of the weights. You can do this for all the weights in your weight vector. You can take the derivative of your objective with respect to that entry in the weight vector and take a step that's large if the derivative is large, because it means that the error function is very sensitive to that coordinate, and it's a very small step if the derivative is small, because when the derivative is small, it means that the error function is not very sensitive to this current coordinate you're considering. Okay, so the approximate Q update can be explained exactly this way. So let's take a close look at the comparison here. We have a Wm that's being updated. It's retaining its current Wm value, but then nudging it in the direction of what we now understand as the derivative of a least squares objective. We're trying to get the Q values to be equal to the Q values they're supposed to be. What are they supposed to be? We actually don't know what they're supposed to be. We don't have their actual Q values, but we have this sample target. So we'll assume that this is our target for our current update. We'll know we'll do more updates in the future and things will get adjusted, but this is our best estimate of a target right now, over here. That corresponds to Y, target. Then we compared with our current prediction. So our prediction here, QSA, that corresponds to this thing over here. That was our prediction before. Okay. So if the difference between target and prediction is sitting right in there, then we see that we get the weighting here by how high the feature values are. We now see that was not an arbitrary choice to make. If you make your update based on taking the derivative of your objective function, you actually get that feature to appear right there. It's telling you that it should appear in this type of update. We do the same thing over here. We have the feature value right there, such that for features where they're very active, the update is larger than features that are not very active. In bigger context, is this the perfect thing to do? If you've seen a lot of numerical optimization already, you'll realize this is effectively gradient descent, what you're doing here, or a stochastic version thereof, because we only have estimates of the target. Now, there are other methods out there that are higher order methods, like Newton's method and so forth, and there are variants of Newton's method that you can just as well apply to QLearning, and that will, in some sense, work better. Practice, the main thing to keep in mind is that to get these things to work well, especially gradient descent, make sure all your feature values are roughly of the same scale. So if some features are always 1 million or negative 1 million, and other features are always between 0.01 and 0.0001, it'll be very hard to get something like this to work. So what you then need to do is ahead of time say, I'm going to redefine my features, and I'm going to make sure they all live in some kind of reasonable scale. Let's say for each feature, you say, what's the maximum it ever is? divided by that, and that way you bring it all to maybe the scale -1 + 1, and then these kind of approaches will work pretty well. Without that though, if the scales are too different, this will be quite slow. So keep that in mind as you define your own features for your project 3 maybe and so forth. You want them to live on the same scale roughly. Now one thing to think about is, well, we cannot express the actual Q values anymore that we ultimately maybe wanted to learn because we're restricted now to use a weighted combination of features. And if we only have a small number of features, or a relatively small number of features, we cannot learn to represent an arbitrary function. For example, this function here, you could say, well, if we try to fit a line through it, it's not going to be a very close fit. Maybe that's not good enough. What should I do instead? Now, I need to be careful on the other side too. If you say, well, I'm going to fit something very complicated through this, right? You might get something like this. That might just not be right either. This is what you would do if you fit something of the form y equals w0 plus w1x plus w2x squared plus and so forth plus w15x to the 15. You have 16 weights there to play with. You can get a much closer fit than a line would give you, but do we really think this is the right value over here? Well, we don't know because we've never seen the value there, but it seems unlikely. For most scenarios, you'd not be very happy with something that predicts something over here for this value and same thing over here. And if you had a line, maybe you'd be happier with that than with this 15th order polynomial. We'll see a lot more of how to avoid overfitting in the one-third of this class. But keep this in mind for now. It's not just a matter of adding more and more features to become more expressive, because at some point you'll overfit. You'll do really well on the samples you've seen, but then on things you have not seen yet, you'll do really poorly. All right, so one last reinforcement learning technique left here. This one is actually gaining a lot of popularity. It's seen a good amount of success, especially in robotics. It's called policy search. In fact, probably one of the very last lectures we'll see some more of this when we look at applications, because a lot of the biggest successes in my group in the last year or two have been using policy search, getting robots to do pretty interesting tasks. Now, the problem with feature-based policies is that even though it's reasonable what we all just looked at with QLearning and can do well in many scenarios, ultimately, when we learn the weights we just described, the way we just described, we are not optimizing the weights for performance. We're optimizing the weights to try to ensure that Bellman equation is approximately satisfied. That on the samples we see, at least, it's approximately satisfied. But ultimately what we care about is whether, if we use the policy that results from the Q function we learned, if we do well or not. And so you could ask yourself the question, wouldn't it be better to try to directly optimize our weights, keeping in mind what the resulting performance would be if we were to use those weights to act in our MDP? And that's what policy search does. It directly looks at how good are these weights if you use them, and then we'll nudge them in the right direction to do better. Okay? So it's a different objective in your learning. The first objective was get Q values that are good Q values. The objective we're looking at now is get weights that result in good performance. Okay, now, so the solution would be to directly optimize those weights to maximize rewards we get. All right. The way you do this is essentially a hill climbing procedure. You start with some weights, you nudge them, you see if you do better or worse. Well, you might have to run multiple times to see if you do better or worse because it's stochastic and the outcomes are not always the same, even for a given set of weights. Then after you realize whether it's better or worse, or likely better or worse, you either keep or don't keep that change and repeat. You can imagine this is not nearly as informed a learning process as we just described, right? It's using much less information, just saying over the entire run, what was the total sum of rewards, and was that better or worse than what I had before? So using a lot less information about your runs. So often what you might do in practice is first you run QLearning, which uses a lot more information, but when QLearning has converged for you, you might tweak your weights a little bit to fine-tune them for performance at the very end. Okay, so the simplest policy search would be you start with the Q function that you already learned, maybe from QLearning, maybe random, but that probably won't be as good, and you run your hill climbing search. Lots of questions there. How do you know the policy got better? How many samples do you need? Do you need to be very sure that it got better, or is it okay to update when you're kind of medium sure it was better? Practice, you often need to run many sample episodes. If you do it in simulation, there are little tricks you can play, right? Imagine you run something, you're trying to learn to fly a helicopter, and the wind gusts are different every time you fly. Now it's very difficult to compare the settings of your weights, because maybe you were in worse circumstances the second time than the first time. However, if you're able to run in simulation, you can simulate the wind pattern to be the same every single time, and now you can compare more fairly between different weight settings. Well, generally in simulation, you could fix all your randomness as you compare weights and have different random seats, so you don't have just one type of scenario, but for each weight setting, use the same set of random seats to compare. So there's all kind of tricks you can play, a little beyond the scope of this class, but I do want you to be aware that they exist. Okay, so let's take a look at the kind of results we can get with this approach. So here, it's actually Andrew Ng shown, the name shown at the bottom here. Andrew Ng is the same Andrew Ng that I showed on the third slide this lecture, who's giving a presentation at 1:30 today in the Wozniak Lounge, who's heading up Baidu research in Silicon Valley, used to be, well, still is a professor at Stanford in parallel, and has done a lot of work on machine learning. This is some earlier work that he likely wouldn't talk about today. He actually was a PhD student at Berkeley before he did all that other stuff. So let's take a look at what's happening here. What was done here? Policy search was run. There was a weight vector W with 12 free parameters. 12 parameters is often too many to set by hand. It's very difficult to kind of just try out all these parameters and nudge them and hope that you get there. So reinforcement learning was run. In particular, policy search was run to nudge those weights. The policy search was actually run in simulation because it takes quite a few iterations. So first the model of the helicopter was built, then that model of the helicopter was used in simulation to run policy search. You find the policy that works well in simulation, then you kind of hope your model is good enough so that it also works in reality. Let's take a look at the result. This is all autonomous. Okay, so what just happened here? Aside from some amazing cinematography, this helicopter is hovering upside down, right? And very steadily so. Just hovering a helicopter in place is actually a difficult task. Helicopters have unstable dynamics. What that means is if you don't continuously adjust your controls, they will drop out of the sky. The simplest way to think of it is, let's say you take a very tall broom, put the non-broomy end on top of your palm and try to balance it. If you have your eyes closed and maybe wearing a thick glove so you can not even feel what's going on with the broom, likely you're losing it pretty quickly. Once you can feel it, once you can see it, it'll be a lot easier. You need to provide continuous adjustments to balance it. That's what hovering is really like. It's continuously adjusting, especially if there's wind gusts and so forth that push your broom around, maybe put a big sail on it to make it harder. That's what helicopter flight is like. So this is able to learn to keep this helicopter in place. In addition, it's able to do so upside down. What's the deal there? Most of you, if you've flown a helicopter, probably didn't fly it upside down. What happens with these helicopters is that you can control them by changing the angle of the blades. So rather than spinning up and spinning down the blades to provide more vertical thrust, you can change the angle. The steeper the angle, the more air gets pushed down. The angle is completely flat, you push no air down. The angle is negative, you push air up, which allows you to go down very fast. Or if you're inverted and you have a negative angle, the two negatives cancel out, you actually get air pushed down again, and you can stay up in the air. It's actually more efficient to fly this way. Any thoughts why this is more efficient? Suggestion there. So the suggestion was actually right on, but I'm going to repeat it so everybody can hear it, is that what happens is you pull in air, you accelerate it, you're pushing this air down, it's going much faster below the blades than it was above the blades. Now if below the blades there's a helicopter body, that much faster air is dragging the helicopter body down, while at the same time the blades are pulling up, of course, because of the thrust they generate, and they work a bit against each other. Whereas if you're inverted, the slow air is pulled over the helicopter body, dragging it down only a little bit, and then the very fast air is not being dragged over anything and fully helps you push up. In general, how this works actually to fly one of these helicopters is you control the angle of the blades to control the amount of vertical thrust. Then you control the angle of the blades also to go forward or sideways. In fact, you cannot even directly go forward or sideways. What you do is you choose the angle to be steeper on the right than on the left, or front or back. That allows you to generate a torque because you push a differential amount of air down, front, back, left, right. That way your helicopter experiences a torque. It'll start rotating. If you want to fly forward, you'll do that to nudge the nose down. Once the nose is pointing down, the vertical thrust in the frame of the helicopter is now not just vertical anymore in the earth-fixed frame, and allow you to go forward. But as far as the helicopter is concerned, the thrust is still vertical relative to the helicopter frame at all times. In addition, you also have a tail rotor. The tail rotor, what it does is it allows you to change the direction you're facing. That's one part of the deal there. Now, you might say, why do I even care which direction I'm facing? For these model helicopters, it might not matter all that much, but there's another reason you have a tail rotor, which is that it actually compensates for the counter torque of the main rotor. As your motor is applying a torque to pull the main rotor around, there'll be a counter torque on the helicopter body. If you don't have a tail rotor, the helicopter body will be spinning the opposite direction of the main rotor, and that can be very disorienting, not to mention that the controls are always in the helicopter frame, and so now you want to move in any kind of direction. It becomes very difficult if you're spinning around very, very fast. So the tail rotor compensates for that, actually in exactly the same way as the main rotor in some sense. There you can also change the pitch angle, and if you make the angle steeper, you generate more thrust with your tail rotor. If you make it less steep, you generate less thrust. Now you don't vary it along the cycle for the tail rotor. It's a fixed angle throughout the entire cycle, but it can be larger or smaller. All right, any more questions about reinforcement learning or helicopter flight at this point? We'll see a lot more helicopter flight later beyond flying in place. Okay, we hit a 1/3 point, so to say, of this class. We've seen everything for part 1, search and planning, also everything that we will be quizzing you about on midterm 1. We've seen how AI can solve problems in search, CSPs, games, MDPs, and RL. Next, we'll start looking at uncertainty and learning. That's it for today.